Thank you very much, and I would like to thank the organization. I'm a bit outside the optimal world, so it's the first time for me at this meeting. And okay. I would like actually to start with something very basic, which is this binding equilibrium we all know between an aptamer and its target protein. I will focus on aptamers binding proteins or bulky molecules in general. So normally, one of the first things we do when we have an aptamer is to characterize the binding equilibrium, the affinity, and also in the binding kinetics. And normally we do that in pure solutions. There are a lot of techniques to do that. If we want to go closer to a more realistic situation, for example, where we have the aptamer and the target protein in a complex solution, like in serum, for example, we would have, in general, something like that. So there is a chance that our aptamer interacts with something else, for example, serum proteins. And normally affinity is weaker than the affinity for the target, but the point is this serum protein are sometimes highly concentrated. So even if we have a weak affinity, their effect might be relevant. For example, on stability, on pharmacokinetics. So it is important also to evaluate this. And what I propose today in this presentation is the use of biophysical technique, fluorescence correlation spectroscopy, FCS, for the characterization in vitro of aptamers binding to proteins in general. This will be done in terms of quantifying usual affinity and kinetics for the target proteins, and also to investigate interaction with off-target components, serum proteins in particular, but at their physiological high concentration. So I'll spend a couple of words on the technique, because maybe it's not familiar to all of you. So essentially, it's set up as a confocal microscope. So we have the laser excitation, which is focused on the sample, which is a drop of solution, which contains, in this case, an aptamer diluted, conjugated with a dye. And then fluorescence is emitted, passes through a lot of optical elements, and is finally collected by a photon counting detector. So what is happening inside the drop is that the actual effective detection volume of this setup is really tiny. It's about 1/4 liter. So the aptamer in the sample is diluted to nanomolar or even lower. And so aptamers are diffusing by Brownian motions. And when the aptamer crosses this detection volume, it will emit fluorescence by a single aptamer molecules. And we can detect this fluorescence. So what is measured is during the acquisition time, these fluorescence fluctuations that you see here. And these fluctuations are due to single aptamer molecules that enters and exit by moving by Brownian motion, enter and exit the detection volume. So if we do an autocorrelation of the signal, we can get this typical output, this autocorrelation curve. It will be our output, and we can get two pieces of information. The first one is the amplitude. Amplitude is inversely proportional to the number of fluorescent species inside the volume. And the second and most important is the decay time of this curve, which is, I call it tau d, is the diffusion time. So the time that aptamer spends inside the detection volume by moving. So it's clear that if our aptamer is bound to something bulky, its apparent diffusion will be slower, and we will see a change in this time. Also, I would like to stress three main features. So the first one, we have a high sensitivity. So we are probing molecules one by one. We are not using a bulk sample. Second, related, is we are using low amounts of products. So nanomolar or even less concentration of aptamer and just a drop of solution. And finally, we are working on homogeneous solution. So we don't need to immobilize molecules on the surface or using pull down techniques or creating gradients with temperature or microfluidics, just using a homogeneous solution. So I will show you now a few results in a case study. we studied this previously known aptamer. I call it SL1, but is also known as clone 3, and is an aptamer targeting a CMAC protein. So we conjugated the aptamer with this fluorophore. And if we place 100 molar of this aptamer in a solution, we measure CS, we get this. With a fitting, we can obtain the diffusion time, 0.57 milliseconds, corresponding to a diffusion coefficient of 90 square meter per second and a hydrodynamic radius of 2.7 nanometers. Now, if in the same solution we place a large excess of the target protein, which is very big, you see there is a large shift of the curve towards longer correlation times. And that means that the aptamer is bound, and now the complex has a slower diffusion. So we see an increase in the apparent diffusion time. And actually, the diffusion time that we measure is 1.1 milliseconds, corresponding to a D of 30 and a hydrodynamic radius of 8, more or less 8 nanometers. Also, the amplitude of the curve is really similar. So this tells us that, at least under this condition, under logic says the stochastic is 1. So, having this in mind, we measure the living affinity. So we started with a 100 picomolar solution of aptamer and started increasing the target protein from 0 to 100 nanomolar. And as you can see, the curve is shifting. The more we add the protein, that means we have an increasing fraction of aptamer that is bound from a complex. So we can calculate the diffusion time for every of this curve, and from this diffusion time we get the fraction bound, which is this green, this green trend here. It increases and then reaches more or less a saturation. These are two controls performed with a non-specific sequence, and this one is done with EGG instead of the target protein. So yeah, actually we can apply this binding model and it worked pretty well, and we got a KD of 5 nanomolar. So we moved on characterizing kinetics, which is something not so trivial indeed. Here the key point is that we are again using low concentration, so subnanomolar concentration of aptamer. Under these conditions, the equilibration is really slow. So when we mix these two components, it will take from tens of minutes to hours until equilibration is complete. So this slow equilibration can be followed in time without techniques. So yeah, here I mix 100 picomolar of aptamer with 5 nanomolar of target protein. And from the time of mixing, I started monitoring the curve. And as you can see, it's again shifting on the right. So we can plot the diffusion times, how they change during acquisition. And well, is this blue plot? It's a bit noisy, but you can see they follow the expected saturating exponential. So from these, we get the equilibration rate for this solution. Now, we know that equilibration rates scales linearly with the target protein concentration. And actually, this was beautifully demonstrated also in our data. So by fitting graph with a linear model, we can extrapolate the K on and the K off rates under this condition. And actually, we got for this complex an average half-life of about 30 minutes. Okay, so we moved on, investigating what is actually happening when we expose the aptamer to serum proteins at physiological concentration. We started with albumin, the most abundant one. So we exposed again 1 nanomolar of the aptamer to a growing concentration of albumin, and you can see here I plotted the observed diffusion time of the aptamer as a function of albumin. This line here is the level of the free aptamer diffusion. And so up to a few hundred micromolar of albumin, nothing happens. The aptamer is all free. Then if we start increasing towards the millimolar, we see a sudden change, but we never observe a saturation. So this is strange because we would expect some saturating something around here. So we attributed this change to a change in viscosity. So the aptamer slows down, not because it's bound, but because the solution is too concentrated. But if we focus on this physiological range, as you can see, there is relatively small shift from the free aptamer level. So we can conclude that basically our aptamer is not interacting at all. And we did the same with 3 other abundant serum proteins like IgG. IgG, more or less, the situation is the same as for albumin. So we see an increase, but it's not really binding. Transferrin, nothing happens. Fibrinogen was strange because we see an apparent decrease of the diffusion time. I think this is due to the interaction with the dye. So it's something with the interacting and changing the photophysics of the dye. So it may indicate that something happens, but again, we don't observe a real complex formation in this case. So, 2 main conclusions from this part. First of all, the technique is able to probe behavior under physiologically relevant serum concentration of this protein. And in this case, for this aptamer, we didn't detect any clear sign of formation of a complex. So finally, the last experiment, we basically performed the same titration with the target protein, but not in pure solution, but in the presence of these 4 serum protein at their physiological concentration. And actually, the results are quite nice. You see the shifting, the usual shifting of the curve, indicating the binding. Here I plotted the average diffusion time, and this is the control with the non-specific sequence. And this was nicely fit, and actually we got the same KD that we had in pure solution. So we can say that at least for this aptamer, these serum protein are not interacting at all. So the affinity is unchanged in our measurement. Well, let me conclude. So I show you these data just to propose FCS as an alternative or complementary tool in this type of aptamer research, especially for binding characterization. Also, perspective, I would like to implement a 2-color FCS approach using 2 colors to study. I think this is very relevant, might be very relevant to study B-specific aptamers or multivariant aptamers. So you can probe if the 2 things go together very accurately. And finally, let me thank all the group at the University of Parma, and also David Torciani, who's helped me with this work. He's the aptamer expert, not really about the transfer. The founding, and all of you for the